In the early 19th century, as science began to unravel the mysteries of electromagnetism, a young British scientist named Michael Faraday made a groundbreaking discovery that would change our understanding of light and magnetism forever. Faraday discovered that when light passes through a medium, such as glass or another transparent material, in the presence of a magnetic field, something rather extraordinary happens. The light waves become bent or polarized, a phenomenon now known as the Faraday Effect. This phenomenon demonstrated that light is not just a wave but also carries angular momentum, forever linking electromagnetism with optics. Today, the Faraday Effect has practical applications in various technologies, from optical isolators in telecommunications hardware, to devices that manipulate light for advanced scientific research. Faraday's discovery not only advanced our understanding of the natural world, but also paved the way for innovations that continue to shape our modern technology. Today, we are going to try and reproduce this effect for ourselves. This channel is by no means the first one to attempt to reproduce this effect in an experiment. We were not content to just record some faint light level changes down the bore site of the experiment. We are looking for a good and strong effect. This is by no means a criticism of other channels that have performed simple experiments to demonstrate the principle. Ben, from Applied Science, represents the gold standard of what amateur experimenters can achieve. We just wanted to make this bigger and better, and see what else we can learn about this effect. Getting some good results from this experiment has taken months. We have been working on this in the background for a bloody long time, and we almost gave up several times. So, sit back, and get ready to watch us screw things up a few times. Hopefully, in the end, the final results, and some of the lessons learned will be worth your investment in time. Light has many properties. One of these is called polarization. Most light sources emit light which is randomly polarized at all possible angles. This is a polarizing filter. It doesn't matter which way it is facing this light source, the brightness is the same. But if we introduce a second one, with the filter arranged at 90 degrees, something interesting happens. The first filter blocks rays of light that are less vertically polarized, while the second filter blocks those that have less horizontal polarization. Together, they basically filter out almost all of the light when correctly aligned. Today, we are going to manipulate this effect to our advantage. So here is the experimental setup. We are going to use a laser as the light source. We will talk more about why a little later. In front of the laser is a polarizer which is arranged to only allow vertically polarized light to pass. Then there is a transparent tube containing the material we are going to test. Around this we have an electromagnet, which will produce a magnetic field down the length of the sample tube. There is a power supply and a switch to allow the effect to be turned on and off. Next there is another polarizer, this time arranged in the horizontal axis. This can be adjusted to find the point of lowest brightness very accurately. This adjustable polarizer is often called an analyzer. And finally, there is a viewing screen, which is little more than a piece of white paper. When the analyzer is adjusted correctly, almost no laser light will fall onto the screen. But, when the electromagnet is energized, the sample material can change the polarization of the light, and perhaps some light will pass the second polarizer and be visible on the viewing screen. To quantify how strongly different materials undergo the Faraday effect, we use something called the Verdict constant. This allows us to calculate the amount of angular change of the polarization, based upon the length of the sample and the magnetic field strength. It should be noted that increasing the length of the sample, or the magnetic field strength, will increase the angular change of the polarization shift. It should also be noted that the verdict constant itself changes in value with the wavelength of light. Well, so much for being a constant. This is why we are going to use lasers for this experiment. We are going to test at several different wavelengths, and see if we can get a wavelength-dependent Faraday effect. Right, let's get on and build some apparatus. Okay, so let's start with some of the wrong turns that this project took. There were quite a few. Our initial idea was that we would test different materials and see how they varied. Our concept called for sealed tubes, containing the liquids to be tested, which could then be inserted into the solenoid electromagnet. I can tell you now, this concept did cause a lot of problems. So, we 3D printed some bobbins to form the solenoid, and then around this, wound the wire. We used solid core wire with a cross-sectional area of 1 square millimeter. This was the easy part. In other videos on the subject, we learned that olive oil has a really high verdict constant, and is ideal for these kinds of experiments. Of course, like complete idiots, we didn't check that assumption, a mistake which would come back to haunt us later. Initially, we used 200mm long plexiglass tubes, with glass end windows. We tried sealing the end windows with a range of different adhesives, UV curing resins, CA glue and 2 types of epoxy resin. None of these turned out to be satisfactory. These would always leak after a day or two. With the olive oil, sometimes this would not even seal at all. We assumed that the leakage occurred because of the different thermal coefficients of expansion of the silica glass and plexiglass. So, we changed the tube to a glass type. This was better, but using olive oil we noticed that for some of the laser types, almost all of the light was being absorbed by the oil. And then disaster struck. When moving the apparatus between home and the office, the tube containing the olive oil leaked. In fact, one end of the tube completely separated. My human assistant's laptop bag filled with olive oil. There was significant collateral damage. The laptop's keyboard needed to be replaced, the bag had to be thrown away, and hours of cleaning was needed for everything else in the bag. But worst of all, a notebook, containing 2 years' worth of lab notes, was now soaked in olive oil. That was in May 2024, and we decided that it was the end of this project. You might ask why there is no footage of those early experiments. You might wonder, if perhaps my silly human assistant deleted it all, in a fit of blind rage. You might well think that, but personally, I cannot comment on such matters. A couple of months later, we re-watched that applied science video, and we noticed that the apparent brightness change in the water sample actually appears brighter than that of olive oil. So, reluctantly, we decided to try again. We just accepted the slowly leaking water from the sample tube, and moved ahead. Incredibly, using distilled water, we were able to see the effect, and it was nice and clear. That made us feel good. Actually, after all the previous trauma, it made us feel really bloody good indeed. So, we got to the serious building. We used an old protractor and a polarizing film as the analyzer, which allows us to measure the angle of the polarization shift. We also changed from the 20 cm long experiment to a 50 cm one. You will recall that the angle of the polarization shift is directly proportional to the length of the medium in the magnetic field. So, we wound a second coil to ensure a strong magnetic field along the length of the new sample tube. We also created a bunch of different supporting hardware, to hold the coils, the polarizers, and the other parts of the experiment, together. Because we are now shining a laser down a pretty long tube, getting the alignments to be repeatable was a challenge. We made some adjustable laser holders to help with that problem. And then we hit another problem, well of course we bloody well did. We noticed that the effect tended to decay after just a minute or two. It was then that we discovered that the plastic polarizer films were being heated, and then destroyed by even these low-power lasers. So, we replaced them with glass polarizers, and this fixed the issue. So now, we are in serious danger of actually having a system that can deliver some results. After all of the problems that had beset this project, that felt like a major achievement. Right, finally it is time to get on, and do some actual experiments with this wonderful piece of equipment. So, now we have a working demonstration of the Faraday effect, we are going to try and make some measurements. First we are going to adjust the output polarizer angle, so that we get the minimum amount of light shining onto the paper screen. Once we have noted the angle, we can then energize the electromagnets and readjust the polarizer again. The difference between these two angles is our polarization shift. We are going to be using 3 different wavelengths of laser light to make these tests. Here, you can see the 650 nanometer red laser in action. And this is a 532 nanometer green laser. And finally, a 410 nanometer violet laser, this one gives the strongest effect. We are going to start with that red laser. We have already nulled out the light, and are ready to measure the shift angle. It should be noted that we are expecting some measurement errors here. We are expecting shift angles that are very small, so using a protractor from a junior school geometry set, is not going to give us high precision measurements. In the end, we got a measurement of around 1.5 degrees for this red laser. Next, we are testing using a green laser. The wavelength is shorter than that of the previous measurement, and so we are expecting a larger shift angle. With our low precision measurement, which is compounded by my human assistant's terrible eyesight, we get an approximate measurement of 2.5 degrees of Faraday rotation. And finally, we will make a measurement with our violet laser. Again, this is an even shorter wavelength source, and gives the strongest effect. Using our crude measurement technique, we get an approximate Faraday rotation of about 4.5 degrees. Whilst none of our measurements are particularly accurate, we thought we would plot these out, and compare with the theoretical values that we should be getting. The solid line at the bottom of this graph shows our results. They are all consistently lower than theory predicts, but there are a lot of unknowns here. For example, we don't really know the actual purity of our distilled water. Given that tap water will give almost zero effect, this could be a significant factor. And then there is the magnetic field. Our winding of the solenoid electromagnets was less than ideal, and this could also introduce some errors. Anything but a perfect winding will result in a lower magnetic field strength than would be calculated. Just for shits and giggles, we reversed the polarity of one of the electromagnets, to see what would happen. We would expect that one of the coils would shift the polarization in one direction, and then the other would shift it back. This is a crude test of how well matched our 2 coils are. With the second coil reversed, we cannot see any Faraday shift being present. And finally, we figured we would show an experiment that is bound to generate some controversy, and hopefully drive engagement in the comments. This effect is often called the three polarizer paradox. We are using polarizing filters, which means that they just block light rays that are not aligned to the filter's polarization orientation. They cannot shift the polarization of light, and they can only attenuate the radiant flux. So, how exactly can adding a third polarizer at a 45-degree angle cause the light intensity of the output to actually increase? Well, there are satisfactory explanations for this effect, using both classical optics and quantum mechanics. But it is still an interesting effect, and very thought-provoking. I have added some links to the video description of some of these explanations. Anyway, we were rather pleased with the results of this experiment. On this channel, successful experiments are about as rare as rocking horse poop. So, despite a lack of basic accuracy, we actually consider this experiment to be rather successful. The effect we achieved is so strong that we are actually not able to perform any direct bore sight photography, for fear of damaging the camera. We have also learned that there is no need to use olive oil to achieve this effect, and that in fact the Verdit constant for this is actually about the same as for pure water. Yes, we had a lot of problems sealing our sample tubes, and didn't get around to testing any other liquids, but we still feel pretty satisfied with the results. Normally, at this point in the video, we discuss how we could improve the experiment, if we were to do it all over again. Let me just make two things clear. Firstly, on this channel, these types of videos about experiments have never attracted a lot of views. Which means that there will probably be very little interest for a video that really doesn't bring any new concepts to the table. Secondly, this was a very traumatic experience for my human assistant, so I doubt if he would be willing to go through this all over again. The fact that we were even able to make some crude measurements of the deflection angle is also pretty satisfying. We think we have identified the main sources of the errors, so anybody wanting to reproduce this experiment can probably get more accurate results. Frankly, the analyzer was pretty limiting, but to construct one that is geared and can be adjusted to within tenths or even hundredths of a degree, sounds pretty challenging. We have also managed to demonstrate the wavelength dependence of the Faraday effect, something that is often glossed over. It would be great if this can be demonstrated with deep ultraviolet, or even low-energy X-rays. The Verdit constant at those wavelengths would be really high. It could possibly allow an X-ray source to effectively be switched on and off in just microseconds. Which would make for a really cool project. Mind you, constructing those kinds of experiments just sounds so bloody easy. Speaking of upcoming projects, our next one is going to be this thermal camera telescope. Make sure you are subscribed if you want to be notified when the video is released. And don't forget to give this video a thumbs up. Anyway, that's all we have for you today. We hope you enjoyed our little video, or at least found some parts of it interesting. If you think we deserve it, then please feel free to give it a like. And you could always hit subscribe, if you want to see more content like this. On the last few videos, we have enabled YouTube advertising. We hate to do it as it ruins the viewing experience, but all of these videos require investments in equipment and materials. We get precious few super chat donations. We would like to thank for following viewers for their donations to our project's fund. It's you guys that really help us to have the opportunity to screw up so many fine experiments. This is still a hobby channel, so we can say what we want, and YouTube's algorithm can go and get f***ed. Thank you for your time. You now have only a very short time to choose the next video to watch.